On Canvas, there is, I think, I hope, a set of slides for today, this week. There it is, modeling.pdf. So if you're a tablet person, go ahead and pull it up. I will do my best to figure out how to get this up now. I have these slides for every module. They are basically outlines of what I'm going to say in lecture. They have, most of the pictures are missing. One, because I'm lazy and it takes a lot of time to draw computer pictures on a PDF. Two, I think there is some value in you getting the pictures with your own hand. Okay? A lot of pictures in this class. My goodness. This is like illustrating for engineers, basically. This is fun. While the PowerPoint's opening, what is this? It's a pencil. Now, what is it pointing at?
Thermostat.
It's a thermostat. This is a control system component that I assume most of you, I mean, we're in California, so maybe not, but it gets vaguely cold here. Occasionally want to heat things up. So we're going to talk about this as a concrete example of a honest-to-goodness control system today. It's an old thermostat, right? You would call this an analog controller. There's no computer, there's no clock. There's not even a battery, actually. Kind of nifty. Yeah, keep bouncing. Come on. So while that's going, oh, hello. Yeah. All right, sweet. So, we are going to talk a lot about how to control systems, and generally step 0 in controlling a system is getting a mathematical model for that system. If you don't have a mathematical model, it becomes really difficult to analytically control something. You can, and a lot of engineering is, oh, here's the thing, what happens when I poke it? Like, you don't need a model for that, but if you want to do anything finely or with nuance, it would be nice if you had a mathematical description of the system. In 228, this took the form of, oh, here's an RLC circuit. Use your knowledge of RLCs and derive the differential equation. Differential equation is a mathematical model for a system. And we learned in 228 that diffie-qs and transfer functions are one-to-one over the space of all LTI systems. So having a diffie-q, having a transfer function, those are the same thing, equivalently. So this is kind of a general, this is not specific to controls, but just general design of systems. You can kind of break it down into a linear process. There occasionally is some feedback, if you will, or go back n steps and try it again. But I'm going to refer to this as the modeling process. So the thing I want to design is likely some kind of physical system. One thing that really helps if you're designing a system is to just get a picture down on paper that helps you name and point to the major components. That would be a functional block diagram. Once you've got the functional block diagram down, and we'll have examples of all this coming up, I just want to give you a big picture. Each of those main components likely has some kind of schematic that could be associated with it. A schematic is a circuit diagram. A schematic is a free body diagram. A schematic is a heat balance diagram. A schematic is a technical diagram, basically, that conveys some knowledge. Right? So I'm using schematic to generalize the concept of a circuit diagram. Okay? Because like it or not, many control systems are not purely electrical. They are electromechanical, or they are electrochemical. They might not even be electrical at all. I don't want to scare you, but there are a lot of systems that have no electrical stuff in them whatsoever. Yeah, sorry. But the stock market is very lucrative, so maybe I get your attention back again. Okay. Once you've got the schematic, and in your mind, when I say schematic, you can think circuit diagram, you can think free body diagram. Once you have that, you can use that to get a Laplace representation of the system. So the 99% of our heavy lifting in this class will be done using the Laplace domain techniques. So once you have a circuit diagram, transform that to the Laplace domain, and you're off and running. That's one of the major learning outcomes of 228. You can do the same exact thing with a free body diagram, with the forces balancing and F equals MA and all that good stuff. Once you've got your Laplace blocks down, you can generally make the diagram smaller. You can collapse Laplace blocks using some techniques that we'll learn. But you know one already, that is a system cascaded with another system. The transfer function of those two systems together is the product of those two blocks. Okay, so that takes two blocks, merges into one, it's the product of those two transfer functions. Once you've collapsed the system down as far as you like, then you can start to analyze and say, oh, if I set this resistor to this value, what happens to the system? Where does the pole frequency lie, et cetera, et cetera. Then you get to ask the actual design kind of questions. Nothing about what I said so far really has any kind of like intelligent design behind it. We're just taking the system as it is, giving it a model, and at the very end, we can analyze that model once we've got all the pieces named and components identified. Okay. You get 10 senior engineers in a room, and you ask them to describe the modeling and design process. They're going to give you 10 different answers. This is one approach. Please don't take it as gospel. Okay, so enter the thermostat. Let's talk about a concrete example of all that stuff. So the goal is to regulate, make constant, the temperature in a room. So step one in this process is determine a physical system and specifications from the requirements. Let's break that down. The physical system is the thing presented to us. We're going to be controlling the temperature in a specific room, which means that room has dimensions. It has atmospheric content. It has wall thicknesses with different compositions. It has numbers of people commonly present in it. Right? The regulation of a yoga studio is going to be different than the regulation of a library carrel. Different kinds of activity go on in those things. The other parts of our physical system might be how big of a heater do we have on hand? Or what are our options for the different kinds of heaters? Are we going to go down the digital electronics road, or are we going to stay analog? Okay. This is one approach to design. It's basically, what do I have on hand? This is like a Gilligan's Island approach. What do we have on hand? What can we make out of it? That is not how all design works. The fancier you get, the more things like, oh, I would really like to do X. Let me produce a thing that does X. That's not this, okay? Those are basically two ends of a spectrum. The Gilligan's Island approach and the, SpaceX approach. I need to do this crazy thing. Nothing exists that does the thing. We need to build a thing that does the thing. Anywhere between, you can imagine a design process that might have some of this and some of that. Okay. your term project is Gilligan's Island. It is, here are the things that you are able to work with, build me something cool. Okay? Cool, get it? Temperature. All right, so we've got the physical system, pieces of it anyway. What should we require of our regulator? Well, some common things that might come up is maintain a set temperature. But also, we should allow the user, whoever that is, to be able to change that set point. Now, right there, we've got some hidden constraints, right? We're not going to let them set it to absolute 0. We're probably not going to let them set it to 150 degrees C. Like, in particular, the people, brought to you by Honeywell, the people that made this said that, oh, we're probably going to regulate between 50 and 90 degrees Fahrenheit. But that was a design choice. Let's see. I'm sure there are others you can think of. In fact, right, maintaining the temperature of this classroom is different when there are 40 people in it than when there are 2 people in it. Okay, so you also probably are going to have some requirements on what kind of variation you can tolerate. Another way to talk about that is what kind of disturbances your system can reject. Right? One way to think about this room is that when it's empty, the thermostat can keep it in stasis. And when all 40 of us get in here and start producing heat, we act as a disturbance on that system. And the regulator needs to be able to account for that. We've all been in classrooms where that fails, usually during a final or something like that, right? All right, so when I say specifications, I usually mean something quantitative, something more engineering than the requirements. Right? These are plain English sentences. When we get to the specifications, those are much more mathy, quantitative, if you will. So an example of these might be keep the temperature within a bounded range, or mathematically speaking, a bounded signal. It would be really poor if our heater, if our control system, for certain initial conditions, just heated the hell out of the room. Right? We would like, an engineering way to say this is make it stable. Right? This is the 228 concept of stability. Another spec might be eventually achieve any set temperature exactly. If I set the thermostat to 70 degrees, I want the room temperature to reach 70 degrees exactly. Within a fixed amount of time? No, that's not on there. It could be on there, but that's not what I chose to set on here. So for LTI systems, we've got all these exponential type behaviors. So what we'll call this kind of requirement in this class is a steady state requirement. If you wait long enough, the system will get you where you want to go.
And so this is even if it goes up and stuff, it's like even if you change some condition, it will still eventually get to that temperature, even if it's like somewhere in the middle of that same temperature.
We'd like, just thinking about this problem, like, yeah, we'd like that to, if I open this little window, I don't want the system to not be able to cope at all. We might need to eventually modify this and say, okay, if I lose 5 watts out of the window, then I can still maintain a temperature. But if I open all the windows and I'm losing 50 watts of heat, we can't do it or something like that. Also, if you set the thermostat to 70 degrees, are you going to go and call the Honeywell company and say, look, I set it to 70, but it only gets to 69.4? oh, you're probably going to be okay with some tolerance. Okay, so when I say exactly, that was a choice of mine. And I'm bringing this up because the term project will involve many of these choices. I'm going to leave lots of them up to you. And where many students falter in the term project is they don't realize that the choice is theirs. They go back and they watch this lecture video, and they have, I see these 3 sentences in their reports, like verbatim. And it means that I didn't really think about what I was saying. They just copied what was on the slide. But this bullet point number 2 could have just as easily been achieve any set temp within half a degree. It would probably sell the same number of units if that was true. And the design might be easier. So think about that. Okay, so we've got a stability requirement, for example. We've got a steady state requirement, for example. The last one is what I would call a transient requirement. This is where time is involved. We'd like the system to be able to go from 50 to 70 within 20 minutes. I picked those numbers out of the air, if you will. And another transient requirement might be, in the process of getting to a set point, never, ever, ever let the room temperature get above 80 degrees. I think that's also a reasonable thing to enforce on the thermostat. Is it clear that these 3 things are all like different beasts? They all live in like different areas of your design brain? This is a stability type requirement. This is a does it get there eventually type requirement. And this is how quickly can I get to do a thing type requirement. So, transient requirement as well. And I just used the word requirement where I meant specification for like the last 10 minutes. So, cool. That'll be fun to edit out. Honestly, you'll find requirement and specification used interchangeably a lot. I tried to make them separate because the specs are quantitative in my mind and the requirements are qualitative. All right. Get my notes out. So we've got step 1, which is get everything in front of you and then get the requirements, basically. Step 2, I'm saying, is look at a functional block diagram. How do all of the big parts fit together logically? Okay? So, as an input to our system, I think it's reasonable to call that the set temperature. It's going to be a signal, so it gets a nice little arrow. I need to, generally, this is true, we need to convert something that humans think of into something that our engineering system can deal with. And the broad name for that is a user interface. Top tip, write the thing first, then draw a box around it. User interface takes the thing that the human can think about and translate it into a signal that our system can deal with. Okay? The output of our system is going to be the actual temperature of the room. The actual room temperature. How do we get from A to B? Well, I think we're probably going to need some way to sense the temperature. Thermometer, if you like. But in general, we're going to need a temperature sensor to take this signal and do something with it. Now, what follows is the this class. And that is, oh, so here, sorry, there's a little bit of a oversell. The room itself is a system. One signal that we can take out of that system is the temperature of the room. The way that we're going to affect or actuate the temperature in the room is with a heater. By the way, I'm doing just the heating problem. The heating and cooling problem is more complicated, but it would be parallel to this heater would be an air conditioner or something like that. So this signal is heat being pumped from our heater into the room. Now, this gap is basically where we're going to do all of our interesting work in this class. I'll say that word interesting. It was interesting to me. I hope it made it interesting to you. The key is that we're not going to heat the room according to this signal, nor are we going to heat the room according to this signal. We're going to heat the room according to their difference. Okay? That's the crux of feedback control. If the set temp is above the sensed temp, should we heat or should we cool?
Heat.
If the reverse is true, we need to stop heating. Okay? There are some other fancy things we can do, like run this through an amplifier, maybe run this through a filter. There's some other fancy things. Those are all going to be systems of themselves. The output of those tells the heater what to do. This is the first intellectual hurdle of this class. We're not going to tell what we call the actuator what to do based on what we want, nor are we going to tell it what to do based on what is currently happening, but rather something to do with the difference of those two systems.
Why is that?
Well, think about it this way. If I ignored the sensed temperature, then I would not know what the current state of the room was. If I ignored the set temperature, the user would be fiddling with it and would just be heating or cooling, irrespective of what they wanted. So I need to somehow use both of them. The difference makes sense because it means that the error, when the error is zero, that's a good condition for us as engineers, yeah? When the error is zero, if I amplify zero, I get zero. If I tell the heater nothing, the heater's not going to do anything, and the room stays put. Okay? So you can scale this signal, or you can filter that, or you can scale this, or you can filter that. But by and large, we need to work with the difference of these rather than their sum or rather than their product, because when this is zero, that means we're doing the right thing. Good question. So this is what I would call, roughly, a functional block diagram. There's no math here, really. I mean, there's a plus and a minus sign. You got me there. But there's no transfer functions. There's just some boxes with some labels. Your turn. Where should I put the open window in this diagram? Is it part of the room? As engineers, would it be nice to have a variable system or have the window be represented by a variable signal? Right? I like my systems as static as they can be, because you change the system, you change the transfer function, you can change everything. If you introduce another signal, We've already got one summing junction. Maybe we can add another. I know I've drawn the arrow coming in, but if I put a subtraction sign here, then this would be the heat lost out the window. Now, it's still much more complicated than it was before I drew the yellow stuff. Before, in the white diagram, one input, one output, and this is a 228-esque problem, yeah? With the accounting for the window, we've now got a second input, which is independent of this input, yeah? I'm over here working the thermostat, you're over here opening and closing the window, and we're not in league with each other in general. So we've got a second input, which I would call a disturbance. Whereas this is generally referred to as a reference signal. We want the system to track references, by and large. We want the system to reject disturbances, by and large. They're both inputs, but they definitely have different characters, yeah? We want to follow that, we don't want to follow that as control machines. If you're going to use something like an electric temperature sensor or some kind of digital sensor here, you also might want to model sensor noise. A sensor is basically something that takes a physical quantity and translates it into a voltage or a current that you can actually do stuff with. A popular way to model that is with additive noise. Now, wait.
Sorry, you said something you will represent as your noise.
If you have a sensor, usually it's going to have some noise. One way to model that is by adding a noise signal onto the pure signal. Adding the noise is nice because if you ever want to simplify your life and say, let's do the unnoisy version first, set that to 0, the summing junction becomes a strip line. It's the same with disturbance as well. Usually what I do is I design the system ignoring this, ignoring that, get something working, and then come back and see what it does.
So why do the two junctions really plus and minus and the valve just has two plus signs? Like that one has two pluses and those two have a plus and a minus sign. It's confused.
Okay, the sign that I write next to the in arrow, think of it as a multiplier. So in order to get the difference here, I want to take the positive version of this and the negative version of that and add them. In fact, in the textbook, I think these aren't empty circles, they are sigmas, or literal pluses. I put a negative sign here because I guess in my mind, it's cold outside. So if I open the window, I'm going to lose heat, but I wanted this to be a positive signal, like a positive step, if you like. So if I open the window, if opening the window corresponds with a step up, this negative sign means it's a heat loss. Yeah? Whether this is plus or minus usually doesn't matter because it's going to be random. So, does that make sense? This is generally what I would call the controller of this system. Okay? So we're doing a bit of vocab as well. Occasionally you'll see the controller just refer to this box, but I think it makes sense. It's often you do the differencing within the control circuitry as well. I've already referred to this as an actuator, but There are a subset of you that won't write anything down unless I do, so here you go. Back to a. This block has a couple different names. I think in your textbook, it's generally referred to as the process block. But there are some older books that call it the plant. This is a holdover from when controls was just coming about and people were trying to literally control industrial plant processes. Like, being told or whatever. Questions? All right, so we're not going to get to the next slide today, but I went to the trouble of stealing this little holding thing from the lab classroom, so let's take a look inside this thermostat. Borrowing, I should say. All right. So the user interface is, it's just this, right? That's how I, the human, tell the system what I want it to do. If I want the room to be hot, I think I move it that way. No, sorry, this is reversed. The hotter I want the room, the further I push this lever. Okay. What does that actually do? Can you get this closer? Or brighter? Okay. Is the glare bad? Can you see? All right. So when I move this lever, it's connected to this pin. So as I move this lever, the center of this coil rotates with the lever. Okay. The coil is what's called a bimetal strip. All right, so we're going to get a little bit into mechanical engineering here, but don't freak out. It's two metals sandwiched onto each other and bent around in a coil, bimetal. One of the metals has a large coefficient of thermal expansion. The other has a smaller. Brass and nickel are two examples. What that means is, as the coil itself gets warmer, the high alpha metal expands more than the low alpha, and the coil coils. Right? The outside gets larger, whereas the inside doesn't get as large, so then it would coil more. The reverse would happen if it was cooled. Does that make sense? If these are both exposed to the same temperature, this one is going to expand more than this one. So that means the coil will unwrap as the temperature goes up, and it will wrap tighter as the temperature goes down. This is a way to take temperature and translate it into angle, if you think about it, which is super cool, in my opinion. All right, so how many of you have actually opened one of these up and played with it? 10%, 15%. What's that?
And the mercury ones too.
Okay, I was not brave enough to bring a mercury one in. So, for those of you who have not seen these before, let me see if I can. Oh, and then the angle of the coil then controls which position the switch is in. Right? This is literally an electric switch that goes from position 1 to position 2 based on the temperature. So if I set the temperature high, this position of the switch would be turn the heater on. And then watch this. As the coil gets warmer, the switch moves to the off position, and that would be turn the heater off. Okay. So, I have no idea how ugly that looked on the video camera, but it accomplished what I wanted it to do, which was to show you that without a computer, without even a battery, we're able to make a switch that senses the temperature. Okay. Math on this on Wednesday. I'll see you then.